Hello Bobcats. In this video we're going to discuss polar molecules and how to determine if a molecule is polar or not. So we talked about polar bonds earlier, but now we want to look at a molecule that has several different bonds in it, or several bonds in it. So first, if the partial charge is evenly distributed, around the molecule, it is nonpolar. Okay, and usually this occurs in symmetric shapes. Okay, so let's look at sulfur trioxide. So we have SO3, and the molecule, the Lewis dot structure for this molecule would be sulfur, double bond oxygen, double bond oxygen, double bond oxygen. And just to review very quickly how I got this structure, there's 24 electrons available in this molecule, and the sulfur go in the center, and so if I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and yes, I do have 2, 4, 6, 8, 10, 12 around the sulfur, but this is an expanded sulfur, and the formal charges are 0, 0, 0, and 0, so it's the most stable of the structures that I could have drawn with the Lewis dot structure. And we notice that it is a symmetric shape. In other words, it's got 120 degrees between this and this and this here. Each of these would be 120 degrees apart. And we also remember looking at the sulfur oxygen bond itself. With this is a 2.5, so this is the partial positive part, and this is the partial negative, and we have a dipole in this direction for the oxygen sulfur bond. So if I drew the dipole for each of these, what we have is, because it's symmetrical, 120 degrees apart, each one of these dipoles, they all cancel each other out, and so this would be a non-polar molecule, even though it does have polar bonds in it, because this is symmetrical and these are headed in directions 120 degrees away from each other, and so they cancel each other out. And so we know that this is a symmetric molecule. Number 2. If partial charge is unevenly distributed, so if the partial charge is unevenly distributed, the molecule is polar. Usually a non-symmetrical molecule, usually non-symmetrical. So let's look at an example. Let's take water for example. So if I have water, which is has a structure like this, this is not symmetrical, and we know that the OH bond is polar because oxygen is a 3.5, hydrogen is a 2.1, and so that difference is 1.4. So this is a very polar bond. And we can think of it as that, okay, so in this case we have, this would be the delta, the partial negative, and this would be the partial positive. So we have partial positive here, and then a partial negative here. So if I were to look at this and kind of draw what this molecule would look like, we can think of it as a shape, let's say similar to this. We got where we have the oxygen up here and 2 hydrogens down here, and this would be the partial negative and this would be the partial positive end. So there's some polarity there. The molecule is polar, with the oxygen end being the negative and the hydrogen end being positive. If you want to even make it simpler than that, you can think of it as this would be the partial negative and this would be the partial positive end. So water is polar, and oxygen is more electronegative, therefore has a higher distribution of electrons. And then the hydrogen is less electronegative, therefore has lower distribution of electrons. Okay. So let's look at this a little bit more in depth. What I'm going to talk about, let's talk about determining the polarity here. So I'm going to look at water again, determining polarity. We're going to look at water, and we're going to look at this a little bit more in depth. So we know, okay, water has a bent shape. Okay, so it's bent. In other words, if I took the shape, it would kind of be like this, where we have a bent molecule. It's bent, okay? And so we know it's non-symmetrical. Okay. We also know that the hydrogen bond is polar, or the oxygen hydrogen bond is polar. If this at 3.5, 2.1, and so we have a difference of 1.4. So we know that the oxygen hydrogen bond is a polar bond, and we would say that it has a dipole vector in this direction from the partial positive to the partial negative. So when I draw this water again, we can say that we have a vector going this direction, and we have a vector going in this direction. Okay, so we have the two vectors here, vector 1, vector 2, and we would, to determine it, we would use what's called vector addition. Now, you don't have to do this. This is just showing exactly what's going on here. Vector addition you'll learn in physics if you ever take physics. But what it is vector addition, I'm going to take vector 1, I'm going to draw it in this direction. So if I take vector 1 and I draw it in that direction, and then I take vector 2 and we do tip to tail to tip, or tip to tail, so I start this tail at this tip and I draw vector 2 in the direction that it's going. Okay, so this is vector 1, vector 2, and then the resultant vector, the one that we were looking at for the whole molecule, would go from beginning to end. So this is the resultant vector, R, and if I drew it over here, my resultant vector goes like this, where this is the partial positive end of the water, and this would be the partial negative end. And so it's the blue, this blue vector here of these vectors, it is the molecule dipole. Not the bond dipole, but the molecule dipole. And so we have a partial positive and a partial negative. So this is a polar molecule. Okay, so this is how I went about determining the polarity of water. So let's look at some other molecules and see how this works. So the next set of molecules that I want to look at, let's look at carbon dioxide. So let's determine polarity of carbon dioxide. So we have a carbon, double bond, oxygen, double bond, oxygen. That's carbon dioxide. We know that the carbon-oxygen bond, it's a 2.5 and a 3.5. So this has a difference of 1.0. So this is a polar bond, and that polarity would be from the least electronegative to the most electronegative. And this would be partially positive here and partially negative here. So we know that this molecule has a polar bond. But when I draw this up here, we have one vector in this direction, and then we have another vector in the opposite direction. And so when I add those two vectors up, what happens is, if I've got, this is the vector addition, so if I have a vector in this direction, and then tip to tail, and I have a vector in this direction, and let's say this is a positive 1.0 and this is a negative 1.0 because it's going in the opposite direction, these two add up to 0. 1.0 plus negative 1.0, that equals 0. So this is a non-polar molecule. Even though it does have polar bonds, it's a non-polar molecule because of the symmetry. And that symmetry, what happens is the vectors add up to be 0. And so it's a non-polar molecule. Again, symmetry is important in determining the polarity of the molecule. So you can have molecules with polar bonds, but they will be non-polar because of the symmetry. Those polar bonds, the polarity of the bonds cancel each other out in the symmetry. Okay, so let's look at a couple of more molecules. In this case, we're going to look at FCN. And the Lewis structure for FCN is F, C triple bond N. We have FCN. So I have to look at two different types of bonds. We have the carbon fluorine bond and we have the carbon nitrogen bond. Now carbon is 2.5, fluorine is a 4.0, so this difference is 1.5. So it is a polar bond, and if we look at it, we have a partial positive here, partial negative here, and we have a dipole vector in that direction. Now for the carbon nitrogen, we have a 2.5 for the carbon, a 3.0 for the nitrogen. That difference is 0.5, so it's not as polar, but it's still a polar bond, and this would be partially positive and partially negative, and the vector, the dipole vector, would not be as large as the other one, but it's still going from the carbon to the nitrogen. So when I go back over here, we know that we have a small vector in this direction, and we have a large vector, dipole vector, in this direction. And so if I take those two vectors and add them, so here I'd have a positive 0.5, and here I would have, remember, tip to tail, so I'm going to go this direction, and this is a negative 1.5 because it's in the opposite direction. And if we took a negative 1.5 plus 0.5, we have a value of negative 1.0. Now the negative just tells you the direction, but we do have a polar molecule because of 1.0. So this is a polar molecule. And when we add them up, if I drew the molecule again, we have F, C triple bond N, and we know that it's a polar molecule. So this is a polar molecule, and my vector, once they've added up, is in this direction. So we know that it's going to be polar towards the fluorine. So this, on this molecule, we have the partial negative here and the partial positive on this end of the molecule. Let's look at a couple more. So the next molecule we're going to look at is boron trichloride. Now, boron trichloride is BCl, Cl, Cl. The shape is called trigonal planar. So this has a trigonal planar shape because it's a triangle and it's on a plane. So these are 120 degrees from each bond going around, and we know it's symmetric because they're all chlorines and they're 120 degrees apart. So this is a symmetric molecule. And if I look at the boron chlorine bond, remember boron, well, let's look at the electronegativity chart. We haven't seen this one yet. So boron is a 2.0 and a chlorine is a 3.0. So we have 2.0 minus 3.0. So this is a polar bond, and the polarity, so polar bond, and that polarity is in this direction. So we've got, because this is the partial positive and this is the partial negative. So if I were to draw that, these vectors here would go in this direction, and in this direction. And so if I look at this and draw a vector addition diagram over here, remember we have one vector going straight up. That's this vector here. We'll call that 1 right here. Then we have vector 2 here, and vector 2 at 120 degrees is going in this direction, and vector 3 at 120 degrees in this direction. So they all end up meeting, and they end up to be 0. So we have a 0 value once because they all end up in the same place. So this is a non-polar molecule, even though it has polar bonds. So this is a nonpolar molecule with polar bonds. Let's do one more here, and then we're going to draw a chart, a decision chart on how to decide if something's polar or nonpolar. Okay. So in this case, though, I'm going to take, and the molecule is going to be a boron with 2 chlorines and a bromine. Okay, so when I draw this, we'll have a boron, and I'm going to draw the bromine on top, and a chlorine here, and a chlorine here. Now, again, we have 2 different types of bonds. We have a boron-bromine and a boron-chlorine. So we have to look and determine the polarity of the boron-bromine and the polarity of the boron-chlorine molecules. Or bonds, sorry, not molecules, the bonds. Boron's a 2.0, bromine is a 2.8. So this has a difference of 0.8. It's a polar bond. And then this one has 2.0, and chlorine is 3.0. So this is 1.0. This is a polar bond. Okay, so we have polar bonds. And if we look at this, this would be the vector would go in this direction, and then these would have vectors going but a little bit longer than this one because it's a more polar. And again, this is a partial positive, partial negative, partial positive, partial negative. And if I were to draw these over here, we would have this vector, and then we would have a much longer vector for the boron chlorine and a longer vector for the boron chlorine. Now, this is a symmetric compound, so these are 120 degrees apart. So if I do my bond or my vector addition, I'm going to take, and this will be 1, 2, 3. So vector 1, I'm going to draw it from here, going down in this direction. Then vector 2 is going in this direction, so I start here, going in this direction. So that's vector 1, vector 2. Vector 3, though, goes up in this direction, but not all the way. And so the vector addition, my resultant vector, would be from here to there. I'm sorry, the other way around. The other way around. The vector would go down because you start from the point and you go down. And so this is the dipole moment of the molecule. That little bit right there is the dipole moment of the molecule. So when I draw that, that dipole moment would be here, and we start from the boron and we go down like this. So this blue one here, we have the partial negative and we have the partial positive. So this is a polar molecule because there is a difference between the bromine and the chlorine. So the chlorine end of the molecule is partial negative, and the bromine end of the molecule is partial positive. So that's how you do it. I'm not expecting you guys to draw vector diagrams. I'm just showing you this. Here's how you are going to make the decisions for knowing if a compound is polar or nonpolar. So let's do a polarity chart or decision chart for polar molecules. So decision chart. For molecule or molecular polarity or molecule polarity. So here we go on a decision chart. First we start here. Are any bonds polar? So we have a decision. If it's no, we're going to go this way. So if it's no, if there are no polar bonds at all, then the molecule is nonpolar. Because it has doesn't have any polar bonds. So molecule is nonpolar. So that's one decision here. Now, if there are polar bonds, so yes, we have polar bonds. Yes. Well, then the next thing we have to ask are atoms symmetrically distributed around central atom? So that's our next question. If we have polar bonds, are the atoms symmetrically distributed? If they are, if the answer is yes, then the next question is, are all outside atoms the same? If the answer is yes, they are all the same, then molecule is nonpolar. And that's a decision. So again, if we're looking and we see that the atoms are symmetrically distributed around the central atoms, yes. Are all outside atoms the same? Yes, they're the same. Molecule is nonpolar. If the outside atoms are not the same, then the molecule is polar. Oops, need to put that in blue. So again, if all the outside atoms are the same on a symmetrical molecule, if they're the same, molecule is nonpolar. If they're not the same, molecule is polar. So back over here, if they are not symmetrical, so if your decision is no, they're not symmetrical, then the molecule is polar. So if you have polar bonds and it's not symmetrical, then it's going to be a polar molecule. If you have polar bonds and it's symmetrical and all the atoms are the same, outside atoms, then it's a nonpolar molecule. If the outside atoms are not the same, then it's a nonpolar molecule. So let's just make a quick list of what the shapes for symmetric and non-symmetric molecules are. So usually a symmetric molecule is going to be linear, and you'll learn about this in our molecular geometry, which is the next lesson. They'll be trigonoplanar, or tetrahedral in shape. And we'll learn about that next. Non-symmetrical or non-symmetric molecules will have shapes such as bent or trigonal pyramidal. And again, we will learn about that in our next lesson. So this is a chart that will help you determine if a molecule is polar or nonpolar. And we will end the lesson there. Have a good afternoon.